Wastewater treatment is a crucial part of any infrastructural system, and billions of dollars are invested in the process yearly. Wastewater is defined as the disregarded water coming from municipal, commercial, and industrial uses. The primary purpose of sewage treatment is to mitigate contaminants of concern such as ammonia, phosphorus, and carbon. These contaminants, if released into waterways, promote perfect growing conditions for undesirable microorganisms that deplete water from oxygen, which is essential for aquatic life to live and prosper, especially ammonia that is considered highly toxic to fish. Wastewater also carries pathogens, pharmaceutical residue, and excessive amounts of specific nutrients that are harmful to human well-being. In this video, we aim to cover the wastewater treatment process at the Cleveland Wastewater Treatment Plant. Redlandshire Council is currently in charge of operating this facility, and the tour was guided by their respectful representatives, Dr. Scott McMurray and David Heap. The plant is located on Wapian Street and is currently servicing the Cleveland sewerage catchment with a total area of nearly 2,250 hectares. Cleveland Treatment Plant has a design capacity for an estimated population of 38,000. However, it is currently servicing an EP of 41,000, which was managed by the capacity buffers installed in the facility. Furthermore, the plant has a design life of 15 years that can be extended to 20 as the catchment area is considered rural. Cleveland Wastewater Treatment Facility runs 24 hours a day, 7 days a week with capabilities of capacity control, as most of the machinery comes in pairs that can be tweaked according to demand. The discharge treated wastewater complies with a site discharge permit, which is in line with the Environmental Protection Act of 1994.
The Cleveland Wastewater Treatment Plant uses a modified activated sludge process for cleaning the wastewater to dischargeable quality, and the process is represented on this process flow diagram. The preliminary treatment occurs at the inlet works where grit and odor are removed from the water. Secondary treatment occurs in an oxidation ditch where microbes remove contaminants and nutrients. The water is then pumped to two clarifiers for sludge settling. Clear water is pumped from the clarifiers to a chlorination chamber for disinfection, and a final dechlorination step was recently added to the process for compliance with site discharge permit.
Inlet works. Inlet works is the first stage of most conventional wastewater treatment facilities. The purpose of this preliminary stage is to remove coarse and fine solids to facilitate trouble-free wastewater treatment in the latter stages of the system. A daily average of 6 megaliters of water is processed through the inlet works, with an estimated 400 to 500 kilograms of solids removed per day. The raw wastewater entering the plant has an approximate total nitrogen concentration of 70.5 milligrams per liter, a total phosphorus of 11.8 milligram per liter, biochemical oxygen demand of 270 milligrams per liter, and finally chemical oxygen demand of 514 milligrams per liter. Cleveland Treatment Plant uses an advanced twin-band screening system with 5 mm sieve openings to filter out larger solids from causing blockage or failures in the system. The band screens are mechanically cleaned by a rotating band which captures the chunkier rags upscreen and dumps them in the rag bin. The collected rag is later transferred to a designated burial landfill. After the water leaves the screening stage, it goes through a vortex grit removal system in order to settle down the finer sand particles and smaller impurities. This is achieved by pumping the water into a specially designed conical tank that triggers vortex movement of the liquid, pushing the grit to the walls of the tank so it can settle down by the forces of gravity into a special bin. The inlet works is also equipped with a hydrogen sulfide H2S scrubbing and ventilation system that alleviates malodorous gas above human breathing level.
In the secondary treatment phase, a BNR oxidation ditch is used. A BNR oxidation ditch is a modified design aimed at nutrient removal using biological means. This is achieved by having an anaerobic chamber before the ditch for phosphorus removal, and the ditch itself is divided into anoxic and aerobic zones for nitrogen removal. The mixed liquor or return activated sludge RAS is recirculated from the aerobic zone to the anaerobic zone to maximize phosphorus removal. Following preliminary treatment, the water flows into the anaerobic chamber where enhanced biological phosphorus removal is achieved. The main principle here is the enrichment of polyphosphate accumulating organism or POAs. The altering aerobic and anaerobic conditions allow the PAOs to store phosphate as intracellular polyphosphate. Phosphorus removal is achieved by separating the PAO biomass from the waste-activated sludge stream later in the process. The water flows from the anaerobic chamber into the oxidation ditch. The oxidation ditch is a modified activated sludge process that removes biodegradable organics from wastewater through long solid retention times. This type of bioreactor consists of a ring or oval horseshoe-shaped channel and is also sometimes referred as the racetrack reactor. The water moves within the ditch at approximately 0.35 meter per second and is aerated along the channel. The ditch at Cleveland Wastewater Treatment Plant is operated on a 24/7, 365-day rotation, has a volume of 9.9 megaliters, and a hydraulic retention time of 2 days. The solid retention time is 18 days. The COD to P ratio is 70:1, and the COD to N ratio is 10:1. As the process used in this plant is aimed at achieving denitrification, the modified Lutzow-Ettinger or MLE process is used, which adds an anoxic zone on the outer track of the ditch. There are 3 vertical surface aerators within the ditch that are mounted on shafts and submerged to 2 meters below the surface. These aerators transfer oxygen from gaseous phase to liquid phase, and the agitation in the water surface is clearly visible in the aerobic zones. Submerged sensors are used to monitor, and the SCADA system is used to maintain the dissolved oxygen at 1 milligram per liter. In the aerobic zone, autotrophic bacteria, also known as nitrifiers, convert ammonia nitrogen to nitrite nitrogen and then to nitrate nitrogen. In the anoxic zone, the heterophobic bacteria convert nitrate nitrogen to nitrogen gas, which escapes to the atmosphere. The water leaves the oxidation ditch as overflow and is pumped to 2 large clarifiers for separation.
The next unit in the treatment plant is the secondary clarifier. The purpose of the clarifier is to allow suspended particles to settle by the force of gravity. This is achieved by slowing down the water flow to approximately 1 meter per hour. The Cleveland treatment plant uses a cylindrical clarifier tank with a diameter of 32.5 meters and a volume of 2.6 megaliters. The feed from the oxidation ditch is pumped through underground pipes and enters the clarifier through centrally located feed pipe. To aid the settling process, alum, a coagulating agent, is added and mixed with the liquor before entry into the clarifier. There are 2 outlet streams in the clarifier: the activated sludge stream, which is composed of the return activated sludge stream, which is recycled back into the bioreactor, and the waste activated sludge stream, which continues onto the dewatering process. The second stream is clear water effluent, which flows over the clarifier. The components of the clarifier include the scum skimmer, the rake arms, the energy dissipating inlet, the feed well, the drive mechanism, and the density current baffle. The liquor is first released into the middle of the tank, where the energy dissipating inlet helps to reduce the flow rate. The feed well helps to navigate the liquor to flow down instead of horizontally across the tank. As the liquor moves outwards from the center, the solids begin to settle and the water flows upwards and out through the overflow trenches to the next process, the chlorination tank. After settling, the activated sludge is mechanically scraped from the bottom by the rake arms and pumped out through the bottom of the tank. This step is done carefully to avoid resuspension. The skimmer is used to remove grease, oil, and other floating materials on the surface. The density current baffle located on the edge of the tank before the overflow trench prevents the scum floating on the surface from entering the overflow trench. Although very clear, the water is not suitable for consumption.
From the clarifier, the clear water is sent to the chlorine contact tank, while the settled solids are sent to the sludge dewatering belt press. The clarified wastewater is pumped through the chlorine dosing system, injected with chlorine and sent to the chlorine contact tank, which is a series of channels that enable relatively still conditions and a sufficient length of time for the chlorine to react with and neutralize any remaining viruses, pathogens, and bacteria that were not removed in the earlier treatment stages. Redland's chlorination design requires 45 to 60 minutes of chlorine contact time. After the water has steadily flowed through the contact tank, an automated dose of SBS, sodium bisulfite, is added to the chlorinated water for instant dechlorination. Thus, chlorine is removed and the final effluent is a slightly salty water, which can be safely disposed into the environment, as it no longer poses a risk of killing essential biota in the natural waterways. For the sludge dewatering, a mechanical filter belt press is used. The activated sludge removed from the clarifier is only 0.5% solid. It is a very wet, turbid mix of the settled flocculants of mostly dead microbes and toilet paper. This removed sludge is called the waste-activated sludge, WAS for short. This WAS is pumped into the belt press receiver tray and mixed with a dose of polymer to further thicken the mix. The sludge mix is then steadily fed between two semi-porous filter belts, within which the sludge material is squeezed through a number of rollers. This compression force works with gravity to remove a substantial amount of liquid and results in a 15% solid material called filter cake. The filter cake is collected and moved by a conveyor belt to a storage bin for further disposal. The liquid removed through this dewatering process is sent to the general purpose pumping station to be pumped back into the beginning of the wastewater treatment system's oxidation ditch. At Redland, approximately 600 kiloliters of waste-activated sludge is dewatered per day, producing 15 tons of filter cake biosolid daily.
The outlet stage is placed immediately after the dechlorination stage. In this stage, the effluent, which has the maximum chlorine concentration of 0.01 mg per liter, are pumped out of the plant in two different streams. 70% of the effluents are released to the freshwater stream in Hilliard's Creek, 2 km downstream from the plant. The other 30% are pumped out to a lagoon, and then it is used to spray irrigation of 68 hectares of irrigating lands. The effluent's quality is strictly controlled, and the process produces a clean and crystal water, ready to be released to the environment. Just for information, the water is not proper for human consumption. The spray irrigation allows the evaporative process to take place and additionally provides some groundwater infiltration. In this way, the plant does not return 100% of the effluents to the water main. As an interesting note, there are some opportunities to improve the water recycling, but they don't have done yet. The solid waste produced is addressed to cotton and maize farms. About the monitoring and control system, there is a Siemens SCADA automated control system installed. It is a standalone system where the plant is not in network with other stations at the same region. The system monitors and controls every single stage of the plant by reading sensors information and running pumps, valves, batchers, machines, and generators. Several sensors are placed at many points of the plant to provide the useful information such as chlorine concentration, effluent flow, pumps and machine status, percentage of dissolved oxygen, and others. The SCADA system also controls the plant's equipment. It doses correctly the chemicals in each step, runs the pumps, injects the chlorine in the disinfection process, and even adds the oxygen by mixing the water into the bioreactor. It also provides a responsive and effective alarm system, coming up with any failure or fault process and even inconsistent readings.
The wastewater and effluent water quality is tested daily by operators for DO, chlorine, pH, BOD, TP, TN, and TSS. The water quality is also tested weekly by the National Association of Testing Authorities per the EPA guidelines. The plant runs 24 hours a day all year round and is currently running at capacity and cannot afford any downtime. To prevent process failure, redundancy is used. For example, there are 2 clarifiers running in parallel. If maintenance is needed to be performed, one of the clarifiers can be taken offline. There are also 2 of each of the dosing pumps, as these are critical to ensuring effluent water quality. The common problems faced by the Redland water treatment facilities are primarily civil, mechanical, and structural problems. One example experienced by 2 other plants with a similar design to the Cleveland plant is a structural problem in the bioreactor. The curved part of the bioreactor is collapsing outwards, which is possibly due to high turbulence caused by excessive aeration. Another common problem faced by the plant is when hazardous waste enters the treatment facility, such as paint. This affects the chemical and physical properties of the wastewater, and consequently the microorganisms which are very sensitive to the environment. This prevents a treatment facility from functioning properly and may lead to poor effluent water quality and possibly eutrophication. The Cleveland plant also has to mitigate environmental issues. For example, the dechlorination unit was installed 2 to 3 years ago to reduce the chlorine content being released into the creek. Once installed, there was an increase in the fish population near the creek outlet, which had previously migrated upstream. Another emerging environmental issue is the increasing concentrations of microplastics in wastewater. The Cleveland plant is not capable of removing microplastics which are less than 5 millimeters in size. Although alum addition helps with settling out the microplastics, they are not fully removed in this process. Lastly, we would like to thank our tour guides from the Redland City Council, as well as Dr. Lee for arranging the tour. Thank you for watching our video, and we hope you enjoyed it.